Welcome to my another interesting video lecture on signals and systems, that is problems based on differential equations using Fourier transform. Today we are going to look at one of the practical comparison with the theoretical aspects or the mathematical aspects of the differential equations using Fourier transform. So we are going to solve the differential equations. It's me, Mohammad Imran sir, from EEE department, MJCT. Now let us look at one of the practical aspects before we dive deep into the solution of differential equations using Fourier transform for today's class. I'm taking aircraft radar system as one of the example. What do you mean by the aircraft radar system? If you look at the system, this is where, over the globe how flights are flying from one location to the other location. This is the overview of the location of the planes over the radar. Now coming to the next slide, let us have a more closer look over single aircraft versus the radar system. Let's say that this red color signal that is going from here left to right is the input signal x of t, and the blue color signal that is coming from the aircraft to the radar is y of t. So all I'm trying to say here is this signal, red color signal, is x of t, and the blue color signal is y of t, which is the outcome or the output from the aircraft to the radar. So these are the two denotions of input and output, and this entire example is a demonstration of signals and systems. You can see how signals input and output are getting transferred between the system, and this shows an explicit example, as I said, of SNS, signals and systems in short. So moving on forward, we have also another view. Let us say that the y of t that is transmitted back from the aircraft to the radar is drawn as nothing but in this way. So the equivalent expression, that is the output of the radar system, the differential equation that we get, is given as d square y of t by dt square plus 5 times of dy of t by dt plus 6 into y of t is equals to d by dt of x of t plus x of t. So this is the differential equation that in today's lecture we are going to solve using Fourier transform. So in conclusion, what have we said so far is the radar gives us the differential equation that needs to be solved using Fourier transform. Coming to the solution of the differential equation of the equation that is being derived or shown previously, d square y by dt square plus 5 dy by dt plus 6 y of t is equal to d by dt of x plus x of t. This is the differential equations that we have, and for this differential equation he says determine the unit step response. So in order to determine the unit step response, we need to assume input as x of t is equal to u of t, and this is the differential equation to which the Fourier transform will be applied on both sides. So in place of x of t I am substituting u of t. So differentiation of u of t is delta of t, and in this case x of t is u of t, as it is u of t is being maintained. Differentiation of u of t is delta of t as the impulse response, and Fourier transform is being applied to the expression on both sides. We get Fourier of d square y by dt square plus Fourier transform of 5 into dy by dt plus 6 into y of t, and Fourier transform of delta of t plus u of t. So we need to know some of the formulas before we proceed ahead. The formulas are nothing but Fourier transform of d by dt of y of t raised to the power of n is j omega to the power of n y of j omega, and Fourier transform of y of t is y of j omega. Fourier transform of delta of t is 1. Fourier transform of u of t is 1 by j omega plus pi into delta of omega. Using these formulas, the substitution of Fourier transform we get. Finally, on application of the formulas of Fourier transform to each and independent terms, we get j omega whole square into y of j omega plus 5 into j omega into y of j omega plus 6 into Fourier transform of y of t is y of j omega plus Fourier transform of delta of t 1 plus Fourier transform of u of t as discussed. So we have just substituted this. We have taken y of j omega common and we have simplified for y of j omega. So this is the expression we get for y of j omega. Further, multiplying the outside terms with each and independent terms inside the bracket, we get 1 plus j omega by j omega into j omega plus 2 into j omega plus 3 plus this expression is in the form of, this term of the expression is in the form of x of omega into delta of omega. And we have a very important property of Fourier transform. X of omega into delta of omega minus omega naught is equal to x of omega naught into delta of omega minus omega naught. And if we put omega naught is equal to 0 in this expression, we can see by comparison that x of omega is x of 0. So clearly omega is 0. So I am substituting for the impulse omega is equal to 0 because of the delta of omega function. Omega value is 0 as per this property. In place of x of omega, it is x of 0. On comparison, omega is 0 in this, and this becomes, by keeping all these terms same, this becomes pi delta of omega by 6. Now considering the part of the expression, entire expression which we have got, for this we are solving using partial fractions a by b by c by, because since we have three different factors j omega plus 2 and j omega plus 3, so in this case it is a by j omega plus b by j omega plus 2 plus c by j omega plus 3. Using partial fractions we will reduce the value of abc, and resubstitution of that abc values gives me the independent terms like 1 by 6 j omega plus 1 by 2 of j omega plus 2 minus 2 by 3 of j omega plus 3. So substituting this part of the expression in the main equation, we get value of y of j omega. Now this y of j omega is in the frequency form that needs to be transferred into time domain. That can be achieved with the help of inverse Fourier transform. With the application of inverse Fourier transform on both sides to the deduced expression, we get finally y of t is equal to 1 by 6 plus 1 by 2 e power minus 2t minus 2 by 3 of e power minus 3t, which is free from all the differential higher orders of the differential equations. Since that we have already evaluated and analyzed y of t, this evaluated y of t can be used for the analysis of time delay. If you look at the red flights, it indicates where the flight gets delayed, how much time it gets delayed, and tells us how far the aircraft is. And if you look at the black color, it shows us the amplitude or the disturbance, and also the green color flights shows us the distortion that reflects the atmospheric interferences with the flights over the radar system. Some of the other applications include weather monitoring systems over the globe as shown in the figure. Finally, I would say the only difference between theory and practical is the power of imagination. I'm not an engineer, but I'm a great teacher who makes great engineers. Thank you.